on KSP. SP stands for solubility product, and we'll find out why it's different. Suppose you take some solid, say silver hydroxide, and you throw it in some water. It will dissolve. There's enough of the solid. There'll be some remaining on the bottom of the beaker, and you'll get sodium ions plus hydroxide ions in equilibrium with solid AgOH. This is a saturated solution. Right over left, K equals Ag plus OH minus over AgOH. But since that's a solid, you cancel it out. So the KSP, solubility, well, it's dissolving, and P, product. There's no denominator. There's no denominators on any of these. So it works like that. You'll notice it's a 1-to-1 ratio. If it was Ag2OH, it'd be a 2-to-1 ratio, and that's going to play a key factor later on when we do this. First type of problem, find the KSP values. Suppose you have some AgHCO3, and it has a solubility of 5.0 times 10 to the negative 7 molar. That's given you, that's the problem. Well, you gotta write a equilibrium expression. AgHCO3 ionizes to form Ag plus HCO3 minus. So the KSP, what this means is you have that amount of molar of AgHCO3 that disappears. It's a 1-to-1 ratio, 1-to-1 ratio. So how much Ag ions, silver ions you have? 5 times 10 to the negative 7. How many hydrogen carbonate ions do you have? Same thing, 5 times 10 to the negative 7. If it was a 2-to-1, this would be 1 times 10 to the negative 6, twice as big. 3-to-1, 1.5 times 10 to the negative 6, and on and on. Now, you take those two concentrations and you plug it in to the KSP. We're assuming X is small and all that other good stuff. KSP equals Ag plus HCO3 minus 5 times 10 to the negative 7, 5 times 10 to the negative 7 equals 2.5 times 10 to the negative 13 is your KSP value for that. Again, same type of problem, except this time we're going to have more than the 1-to-1 ratio. So you have SRF2, and the solubility of that is 1.0 times 10, 1.0 times 10 to the negative 3 molar. Equilibrium expression, SRF2 equilibrium, SR2 plus 2F minus. It's a 1-to-1 to 2 ratio, so this will be 1 times 10 to the negative 3, but this is going to be 2 times 10 to the negative 3. So that's your concentrations. And now you plug it into the equilibrium expression. KSP SR2 plus times F minus squared. And that's another difference. Now you'd think you'd be using it twice, where you double it to get the concentration and then you square it. No, not at all. This is just getting you how much you have. And now here you're going to do the equilibrium expression. So now you plug in what you know. 2 times 10 to the negative 3 squared. Calculator. 4.0 times 10 to the negative 9 is your KSP value for that equilibrium. You can find the concentrations doing the opposite. Another type of equation reaction. Now you're trying to find the concentration of the silver and dichromate ions. Find the concentration of the silver and dichromate. And the KSP is given to you as 7.0 times 10 to the negative 12. Well, here's another case where you start off with the equilibrium expression. These two ions are coming from silver chromate, Ag2C2O7, falls apart to form 2Ag plus Cr2O7 2 minus. The ratio is a 1 to 2 to 1. Now we don't know the concentrations, so we use X. This is 2X, and that's X. If it was 2 and 3, it would be 2X and 3X. Again, that just gives you the concentrations. Now you plug it into the equilibrium expression. KSP silver ions squared dichromate ion equals 7.0 times 10 to the negative 12 equals 2x squared times x, 4x cubed. Divide by 4, because you have to do is 4. Divide by 4 and take the cube root, you get x being a value of 1.21 times 10 to the negative 4 molar. Now I'll bring it back over here. This is going to be 1.21 times 10 to the negative 4 for the dichromate, and double that, 2.42 times 10 to the negative 4 molar for the silver. Everything up to this point, we've had one source. You've had a handful of solid stuff put into the solution that it's coming out. Now we're going to have more than one source, which makes things different. Common ion. All of these up above, you've been throwing in the stuff into pure water. Now you have a solution. You're putting into a solution that contains one of the two ions already present. What is solubility of silver phosphate which has a KSP value of 1.8 times 10 to the negative 18. In 0.100 molar silver nitrate solution. Now the common ion is a silver. Equilibrium expression, or KSP expression, just go straight there, equals the silver ion cubed times the phosphate ion. Well, what do we got? We got Ag3PO4 equilibrium, 3Ag plus PO4 3 minus. This is going to be 0.1 plus 3x. Now we're assuming that 3x is very small, so we're going to call this the 0.1, the assumption. This is x. So when you plug that in, you get 0.1 cubed times x is equal to the KSP so you cube that and divide, that will make that bigger, so it's x is equal to 1.8 times 10 to the negative 15 molar. It's all correct. Sometimes the x is to the first power, sometimes the x is not, as in this case, but it will still do that. Similarly, if you have the anion being able to react with an acid or a base, bicarbonate here. If you have an acid or a base, the acid will make more of this stuff and it'll reverse the equilibrium a bit. If you had a base, it will eat up some of that stuff and it will produce that. It will shift it to the right. So the pH may affect solubility if it reacts with the acid or a base, the form of the two ions. And the last type is will a precipitate form. So will a precipitate form if you mix two different solutions together and one of and they form a precipitate. So what you have is 50 milliliters, for example, 50 milliliters of 0.5 molar cobalt nitrate is mixed with 200 milliliters of 0.04 molar sodium hydroxide, and the KSP for cobalt hydroxide is equal to 2.5 times 10 to the negative 16. Okay? Well, first off, you got to figure out how many cobalt ions, what's the concentration of the cobalt ions, and then you got to figure out what the concentration of the hydroxide ions. Concentration is moles per liter, so you got to take the volume in liters times the molarity, To find the concentration, after you mix them together, you got to divide by the new volume. So, and this is in liters, so 0.05 liters times 0.05 molar divided by the new volume, which is 0.07. Now we give you the concentration of the cobalt ions. Now you got to do the same thing for the hydroxide ions. Oops, not 20 milliliters. So 0.02 times 0.04 divided by 0.07. Doing that math, you will find out that this is 0.0036 molar. Doing this math, it's 0.0011 molar. Notice that the volume increases 0.05 to 0.07, so the total volume is the summation of that. Now you plug it into the KSP expression. It's a 2-to-1 ratio of 1-to-2 ratio of cobalt to hydroxide because that's the charges. So the KSP equals the cobalt ions times the hydroxide ions squared. And what you're doing is you're checking that. So the KSP was given to you as 2.5 times 10 to the negative 16. How does that compare? It's like a Q value, really, to this. And it is 0.0036, 0.0011 squared. How does 2.5 times 10 to the negative 16th compare to 4.36 times 10 to the negative 9? Well, this is much smaller, so there's lots of stuff. There's more stuff in solution than it should hold at the maximum. So yes, precipitate will form. Yes, a solid will form. If you had the other way around, if it was 4.3 times 10 to the negative 17th or 18th, or something like that, then the answer would be no. So if the value here is bigger than your KSP, then yes, a solid will form. If your calculations show a smaller number, then no. It's not a saturated solution, so no solid will form. That ends this lesson on precipitation.